Well, thank you very much. My pleasure. And here's a slide, just kind of a background of my history. Graduated from, actually born and raised in Long Island, New York in USA. Bachelor's of Science in Electrical Engineering. 1990 moved to Madison, Wisconsin, working for a company called Nicolay that manufactured high-speed, high-accuracy data acquisition products. And here I am, about 4 acquisitions later, as I like to say, but proud to have enjoyed the applications engineering position, get to see a lot of different applications each and every day. Looking forward to seeing one today as I do this now from Cleveland, Ohio. And let's move forward and take a look at our agenda today. So basically, the electric drivetrain, making measurements on the electric drivetrain has its challenges, and there are a number of solutions. So we're going to focus mostly on the current measurement, but we'll also talk a little bit about the voltage, the torque, the speed, and Ethernet signals as well, since they also come into play. So we'll be talking about cabling, EMI, grounding, parasitic currents, magnetic fields, measuring small currents, and things centered around those areas. So near the end, we'll talk a little bit about the near future and handling measurements of even increasing voltages and switching frequencies in the electric drivetrain measurement field. We'll provide some links, and then we'll have that can provide you with more details, and then we'll have a Q&A session. So here's somewhat of a typical electric drivetrain measurement setup, if you will, where you have, let's say, a power analyzer. Ideally, it should be a dynamic motor power analyzer. And there are many different types of signals that are analyzed, if you will, ideally recorded so you can go back and do some analysis. So if everything from voltages and currents, not only from the power source, but also from the inverter, maybe making temperature measurements, making torque and speed measurements, maybe some NVH for further development in that area as well, vibration measurements, and often communication protocols involve Ethernet cables. So we'll be talking about those kinds of things as well. So this would be a typically clean cabling for power measurements. You have a power analyzer. It may have some interface to an automated system that's operating the entire test, including the dyno, the motor, etc. And the power analyzer is making measurements on currents, ideally from CTs for high accuracy, using a power supply, making measurements from currents from the battery, the inverter, as well as voltages, and then maybe some torque and speed measurements as well on the electric motor. However, this is more of what you end up seeing in reality. Lots of cables rolled up, maybe crossing other cables. It ends up being a very noisy environment as well. So that's the reality that we're often dealing with. So problems with this typical cabling setup involves dangerous voltages, naturally voltages that may be near 1,000 volts, maybe even more. And then you also have EMC issues. Those are, of course, from pulse width modulated voltages from the inverter, and there could be some other issues as well that are generating some noise in the environment. So this typical cabling is challenging to try and mitigate some of these issues with high voltages for safety, and then also trying to mitigate the noise from EMC voltages, currents, etc., both at the power analyzer and also at the measurement point. So first, let's talk a little bit about minimizing electromagnetic interference. So when you're doing an electric motor test, you have naturally, in most cases, an inverter. You have variable speed drives, and maybe some other electronic equipment, just generating lots of high energy frequency electromagnetic interference. in the lab. And so some tips on reducing the electromagnetic interference and ensuring a more accurate measurement would include keeping all your current cables. So cables that are measuring current should be kept away from cables that are measuring voltage as much as possible. As an example, maybe 3 meters would be a reasonable an example, if you will. Now, it's also suggested to keep the mainframe, your power analyzer, away from the device under test as well to mitigate issues from entering into your power analyzer by at least 3 meters. And you want to be sure and use the right length of voltage and current cable and try to avoid rolling up the cables, because when the cables are rolled up, high frequency electromagnetic interference induces currents and it adds noise to the signal. As you see here in the picture, you want to try to avoid rolling up your cables. And ideally, it's best to just try and have cables that are the appropriate length so they're not laying everywhere, rolled up. And if for whatever reason you find the need that you have to cross voltage and current cables, try to do so perpendicularly to minimize crosstalk. So let's talk about the current sensor cabling, one of the major focuses of this webinar. So some issues that you have, whether it be unshielded measurement cables or shielded measurement cables. First, with unshielded measurement cables, you're subject to electrical noise, obviously. There's high frequency inverters, pulse width modulated voltages, and that's just going to enter into your cable, and basically you're going to have noisy measurements. Even with a shielded measurement cable, which carry currents, the center conductor has current. However, also the outer shield has current. So your current sensors will be measuring the sum of the center conductor of the cable and the outer shield together. So the problem here is that how do you measure the current in a shielded cable and avoid from having to measure both of these currents? So here is a theoretical solution. So what you do is you route the shield around the sensor, ideally in a metal enclosure like you see here. This way, only the center conductor is measured, and the noise is still suppressed by the shield because you're still using the shield on the cable outside of the metal enclosure. So the sensors ideally should be in an EMC cabinet, and the cabinet should be grounded, as well as the CT, and we'll talk a little bit more about that in a moment. And ideally, you'd like to have the cables run straight through the sensor or the CT. Here we see a practical solution where the DC and AC signals are measured separately, and they're installed separately in their own separate metal enclosure. So you have for example, the DC signal on the left for current, and then on the right, a separate metal enclosure with the AC signals on the right. So theoretically, what you're creating is a Faraday cage around the measurement, helping to mitigate noise, electromagnetic interference from entering the measurement and improving accuracy. So now let's talk about the grounding of your CT. So a typical common mode noise source is the high rise time of voltage signals, DVT, in the electronic power switching circuits such as inverters. And between the two conducting elements, you have a stray capacitance. And if the two conducting elements change in potential, you're going to have stray capacitance, which needs to be discharged to match the voltage difference between the two elements. But discharging stray capacitors results in parasitic currents. So if the metal housing of the CT is not grounded, then the parasitic currents are going to run into the sensing head back to the CT power supply. And then you're going to have unwanted side effect. Basically, the current transducer, the CT, is going to measure parasitic currents as measured currents. So to avoid this issue, you want to ground the CT housing. which is going to deflect the parasitic currents to the housing and direct it to Earth. So as the parasitic currents no longer run through the sensing head of the CT, the measured current will not be impacted. Let's talk a little bit about return conductor free zone. So the magnetic field from the return branch of the primary current or adjacent conductors, for example, let's say the remaining phases of a three-phase configuration, it's going to create an imbalance of the sensing core of a flux gate current transducer, and that's going to result in measurement error. So to minimize the error caused by the return conductor, you want to be able to maintain a return conductor free zone. Here's just an example of some suggested spacing that you would want to consider based on a variety of different sized CTs, so 200 amp, 400 amp, 600 amp, and so forth, just to get an idea. Now, sometimes you're having to measure a small current. Maybe the dyno is operating in a no load condition, and so currents are not as high as they normally would be. They're going to have significantly low currents in that case. And one solution is to use multiple primary turns. So ideally, as an example here, we have, let's say, a 600 amp CT with a linearity error of, let's say, 1.1 ppm. Basically, it's 0.6 microamps on the secondary or 0.9 milliamps on the primary. So excluding offset error, the accuracy at the primary current, for example, 10 amps will be 0.009% or 90 ppm. So to reduce the impact of the linearity error on small primary currents, multiple turns of the same conductor can be measured by a single CT. So it becomes a little bit convenient here to do that. The CT will measure the number of turns times the conductor current. So for example, if you're using 50 turns of a 10 amp RMS CT, it's going to measure 50 times 10 or 500 amps RMS. Linearity error will be reduced to 0.9 milliamps on 500 amps, so 0.0018% or 1.8 ppm. So to achieve the best accuracy of a multi-turn current measurement, you also want to be sure to have regular repartition of the turns around the hole, as you see here in the diagram, to avoid unbalance or local saturation of the magnetic core. So a practical solution here, not including the Faraday cage scenario, but just to talk about the cabling, you should have shielded cables from the transducer, and that would normally be connected to the measuring unit. So that's going to create a Faraday cage in itself with the shielded cables. And ideally, again, as I mentioned earlier, you want to have the shortest cables possible to mitigate noise issues. So to elaborate a little bit further, let's say in this case, you're using zero flux current transducers, whether it be 50, 200, 400, 600, or 1200 amps RMS. The CTs I've shown here are HBM branded, but they're from DataSense. That's no secret. You'll see that on our website at hbm.com. They provide very high accuracy, up to 0.01% at 5 kilohertz, for example, and even high bandwidth up to as high as a megahertz. And then naturally, you'll use an interface or a power supply unit to power the CTs. And then you have connection cables that run from the CT to the interface or power supply unit. And then you have cables that run from the interface unit or power supply to your dynamic power analyzer. And in all cases, these cables are shielded. We're going to get to some of the other signals that are often measured in an eDrive electric drivetrain measurement. But before we talk about those, let's just kind of provide a quick overview of what a typical solution should be considered for making measurements in an electric drivetrain. So for example, here at HBK, we offer a really nice complete package from sensor to the power analyzer and all the way through to the analysis. So what you have in this particular case, configurable and expandable mainframes, and some really nice packages. Most common packages, a lot of customers are using anywhere from 3 to 9 power channels, but you do have customers once in a while that need to expand to higher counts, and this solution here can expand up to 51 power channels if needed. But the important thing is that you want to save time and money, and so recording the data so that you can review it in further detail later on without having to do the test again, because lab time is very expensive and time consuming. You want to be able to continuously stream the data in most cases for a continuous measurement, or even store the per set point data in real time. And for flexibility, for quite a wide variety of setups, you want to be able to do multiple torques and speeds, and ideally you want to be able to, in this particular configuration, it's capable of doing 12 torques and 12 speeds, and you want to use frequency inputs for maximum accuracy in mitigating noise, and we'll talk more about that in just a moment. The focal point of this measurement is through this power card. It's got 3 voltage inputs and 3 current inputs. So the voltages on the card can be measured directly up to plus minus 1500 volts with a 1000 volt CAT for safety. And there's also high accuracy burden resistors within the system for measuring currents using a CT. Sample rates are up to 2 million samples per second. We find that most customers only really need to do maybe 500 kilohertz, or should I say 500 kilosamples per second. And when increasing to 1 or 2 megasamples is not really a significant change in the results. So regardless, the card actually is sampling at the maximum sample rate all the time anyway, to mitigate aliasing issues. And if you select a slower sampling rate, it's just giving you every other point or what have you. But you get a bandwidth of 1 megahertz on, and this is on every channel. You get a high power accuracy of 0.015% on the reading and 0.02% on the range. And the nice thing here too is that you have many formulas that are supplied right off the shelf for things like space vector, DQ0 transformation, and of course all the usual RMS calculations. But you can add your own custom programmable math, and all the formulas, the ones that are provided and the ones that you create, are all transparent and easily editable. Now, it's also important to have high accuracy and high bandwidth torque, so you can measure things like torque ripple. So, for example, the most accurate torque sensor in the world is actually made by HBM/HBK. HBM's the brand, HBK is the company. And also high accuracy and high bandwidth zero flux AC/DC CTs, for example, 0.01% accuracy up to 5 kilohertz. And you want to be able to have some powerful analysis, both in real time and in post, which is provided right off the shelf, so that you can just click a couple of buttons and away you go in creating efficiency maps, space vectors, DQ0 transformation, torque ripple, harmonics, back EMF, etc. A lot of that is already provided off the shelf, standard. And then you want to be able to integrate your system, your dynamic motor power analyzer, with your dyno. And that can easily be done through a variety of methods, whether it be EtherCAT, CAN-FD, API, XCPOE, Python, TTL, and many others. So either of these can easily be integrated with your dyno system. And there's a lot of integrators that we recommend that use our system for dyno electric drive setups that integrate through a number of these different paths, whatever one is most convenient for you. And then you want to be able to have inputs other than just voltage, current, torque, and speed. If you're also doing NVH, or you want to make measurements of temperature on, let's say, the motor, the inverter, or some CAN signals. Maybe you need to record some signals that are faster than a megahertz. There's 250 megasample per second cards as well. So just about every signal you can imagine can be recorded in sync with your voltage, your current, your torque, and your speed signals, and recorded to the hard drive in real time. Real convenient, because then you can always go back and do more detailed analysis and compare data that you've had maybe recorded last week, the year before, with data that you've recorded today. Now let's talk a little bit more about some of the other signals that are being recorded and how to mitigate noise and maximize accuracy. So naturally, on voltage cables, you would want to have a shield as well. Here's an example of cables that we also supply for the high voltage that can measure 1500 volts DC Cat 3 with a safety rating of 1000 volts Cat 4. 3-phase, all in one cable to make it easy to connect your 3-phase signals. So here you can see the yellow cable here is your shield connector. And so this three-wire shielded cable is going to reduce your electromagnetic disturbance from high power inverters and emissions from rise times of the switching inverter voltages. And conveniently, this cable connects to the power card, as you see here on the right. But if you do need to measure voltages higher than 1500 volts, there are solutions for 5 kV RMS, which conveniently works in conjunction with the power card you see here, providing 0.1% typical accuracy. And there are also solutions for higher voltages than 5 kV. So just let us know if you happen to have concerns or in the need of making voltages higher than 5 kV. We have quite a variety of solutions available depending on the level of your voltage. So this power card, as you see here, also is married nicely for convenience with an artificial star adapter, which basically artificially is providing you the star of the motor. But this measurement technique, however convenient, assumes that the system is balanced. And of course, that's not always the case. Ideally, for the best and most accurate measurement, you would want to use a phase-to-phase line-to-line connection, which you can certainly do with this cable using 3 basically stacking banana cables at the inputs to feed the different phases to more than one channel. And then you can connect the mainframe's ground lug to the cable shield. Some alternatives for cabling, depending on your application. Sometimes if bandwidth is more important than accuracy, or if you don't have any room for a CT, you can use a current clamp or a Rogowski coil. Keep in mind, though, that you do have lower accuracy with current clamps and Rogowski coils, and Rogowski coils only measure AC, not DC. You can conveniently use these different alternatives for measuring current with the power card as well, using a nice shielded cable that provides a BNC output for a BNC input for this particular power card. Now let's talk a little bit about torque and speed and cabling and signals. A lot of times I'll see customers using analog signals for torque, for example, and unfortunately, a lot of noise is married up with a lot of these torque signals because of the issue that analog signals are known to have not as high of an accuracy as you would with a frequency or digital signal, which are immune to noise and offer a much higher accuracy. So ideally, you want to use a frequency or digital signal with appropriate shielded cabling, of course, to mitigate the noise issues that you would have, let's say, with an analog signal. So you can realize the highest accuracy for measurement of torque and speed. I mean, if you buy a high accuracy torque transducer, especially the most accurate one in the world being the 0.007% I've mentioned previously, if you use the analog output, you're just not realizing the accuracy of the torque transducer by using an analog connection. And I hear every once in a while a customer calling up saying they start their electric drive test, and all of a sudden the communication to their power analyzer is lost. And the first thing I mentioned is, well, do you have or are you using shielded Ethernet cables? And that's usually the case for the issue. You get high EMI environments, especially from the pulse width modulated signals coming out of the inverter, and you need to make sure that you're using shielded Ethernet cables to achieve noise immunity. So at minimum, I suggest using shielded Ethernet Cat6 or greater cables, and as you see in the diagram here on the right, the top one has the metal shielded Ethernet connector on there, compared to the one I've placed a red X through, typically the plastic styled Ethernet, which is not shielded at all. So ideally, the connection that you want to ultimately consider is using a fiber optic Ethernet solution for the ultimate noise immunity, and you're going to gain isolation from the high voltage and current environments. So you'll be able to isolate the 2 points of that Ethernet cable through a fiber optic connection. All right, so let's go forward here. In the near future, and even now, we're starting to see increased voltages and switching frequencies in a lot of these electric drive tests. You've probably seen or maybe involved yourself with battery voltages on electric vehicles just going up higher and higher, and this increased level of EMC is emitted and thus increases the EMC problems. So this is going to require higher safety levels, and you want to be sure that the power analyzer that you are using is going to meet the needed voltage level and the over voltage categories. So just a side note on over voltage categories, most of the automotive test rigs are Cat 3 installations. So you want to make sure that your power analyzer is certified for this measurement, especially since safety should be the #1 concern. So there are many power analyzers on the market, most of them just traditional power analyzers designed for making 60 hertz measurements or 50 hertz measurements at a substation, and really can't make measurements when the motor or inverter is changing in frequency. But outside of that, they're only certified for Cat 2 or to very limited levels in Cat 3. So you want to make sure that they are certified to the voltages that you are measuring to make sure that you are focusing on safety, not only for the equipment, but most importantly for yourself. So switching frequencies for battery electric vehicles are going up. So that's increased slew rate, leads to more EMC emitted, and thus increases EMC problems. You have increased sensitivity for long cables and cable capacitance, and that's going to further limit bandwidth, and increased measurement errors caused by increased reflections. So today's solution that you see commonly in an electric drivetrain measurement setup may look something like this. So basically you have issues with high voltage, you have issues with EMC and EMI, and so it's going to become even a greater problem with higher frequencies and higher voltages as we move forward. So here's a new concept with voltage and current satellites. Just think about it. So if you had, let's say, a shoebox-sized measurement device, let's say your amplifier and your digitizer is close, very nearby the measurement point. And then you fiber optically send the results from the amplifier back to your main frame or your power analyzer. That way, you have uncompromised safety. It's going to eliminate EMC issues. You're going to have higher accuracy because you'll have shorter cables, and then you'll have less reflections in your cable. And even, let's take it a step further. How about integrating the CT power supply into the satellite module? That's going to eliminate extra cabling. So this distributed setup with cable lengths maybe up to 500 meters, because the fiber optic cable length really is not a major concern. And even if you have different cable lengths, you want to have a system here that will automatically basically account for any delays that you may have in your fiber optic cables. Maybe you have shorter fiber cables on one box versus your fiber optic cables on another box. You want to make sure the system will also compensate for different cable lengths so that everything is in phase and in sync. But ideally, what you have here is an ultimate solution for not only safety, but also for accuracy and mitigating noise. So as you see here, the satellite-based power measurement concept is going to remove many of the issues that you would have for high voltage safety issues and high frequency EMI issues. They're predominantly centered on the area between the measurement point and the satellite module. And you can minimize those cable lengths because you can maximize your fiber optic cable going back to the power analyzer. So quite an ideal scenario of making a measurement. A little bit more on the fiber optic satellite solution here. So starting at the top here, you see a fiber optic satellite for voltage measurements. So here's a box with 4 individually replaceable voltage input channels, 5 input ranges up to, instead of 1500, now you can measure up to 2000 volts directly. Sample rates traditionally at 2 million samples per second, as we mentioned previously, but an option to go to 20 million samples per second because of the higher frequencies that we're seeing moving forward. More importantly for safety, not only for the equipment, but for yourself, the CAT rating differential at 1500 volts DC and 1000 volt CAT4. And the CAT rating input to chassis at 1000 volt CAT3 and 600 volt CAT4. Now let's move over to the current measurements. Again, 4 individually replaceable current input channels, and then 6 current input ranges up to plus minus 2 amps with precision burden resistors. And naturally, the CTs would make the high current measurement and reduce it down to the plus minus 2 amp on the secondary, going to the actual satellite for the current measurement. Again, sample rates at 2 million samples per second or up to 20 million samples per second if you decide that is necessary for your measurement as we move forward with higher frequencies. And then even an optional built-in CT power supply, which really mitigates the extra cabling needed going into a CT power supply, coming out of the CT power supply. You just connect directly to this satellite module, and it already has the built-in power supply to power your CTs. No extra cabling required. So here we see the receiver card at the other end of the fiber optic cabling. It can actually accept up to 2 satellites, so you've got 4 power channels. You have up to 500 meter cable length capability for the highest user and instrument safety, and practically no EMC issues due to the optical isolation and transmission. So you're going to achieve improved accuracy due to the reduced noise, crosstalk, and the reflections that you would normally have in typical cabling. Ultimately, this would be a solution for making measurements on all possible signals that you would consider in an electric drive measurement, from voltages, currents, torque, speed, temperatures, NVH, etc. All mitigating the issues with the shortest cables from the measurement point to the satellite, and then as long of a cable as you would need on the fiber optic from the satellite back to your dynamic motor power analyzer. So if you're looking for more details on some of the solutions that I've outlined, you can go to www.hbm.com/eDrive, and there you'll see an introduction. There's even an introduction video that talks about the eDrive solution using a dynamic motor power analyzer, and many other things that I've mentioned. However, at any point in time, if you do have questions, you can always contact our HBK technical support personnel, whether it be in North America at support@usa.hbm.com or worldwide at support@hbkworld.com. With that, here's my email address if you need to contact me directly. Thank you, everyone.